And let me tell you this, 100% of time, 100% of the time, 100% of time. What is the only formula you need to know? Is that sine formula. That's the only formula you need. So here, let me write. So you know what? Let me go. You know what? Yeah. So basically, what's the formula you need? The only formula you need is this guy. The limit of what? The limit of sine x that over x as x approaching 0. So it doesn't matter what variable you use here. All of these other guys right here, they follow from this guy. So if you have any kind of limit, the first thing is you check whether it's an indeterminate form or not. If it's an indeterminate form, and then you see that there's a trig function. Now when you look at this from right here, this limit from, oh, there's a cosine there. So that involves a trig. Okay, there's a trig. It can be any trig function. Sine, cosine, tangent, cotangent, secant, cosecant. Any of the trig functions. When you see this here, when you have any limit involving any trig, then what you do? You will be applying this what percent of time? 100% of time. And this is not the one of the many formulas you need. This is the only formula you need. That's there. Is that a good notion? So any kind of limit problem, you have a trig, then you use this formula. 100% of time. And you don't need any other formula. Okay, so now we come to this from right here. There's a limit. Okay, this. Okay. So that's the limit. It's an indeterminate form. And note that there's a cosine theta. Even though there's a theta here as well, but there is a trig function involved here. So what is that we can do here? What do we do? What do we do? So this is now going to be this. The limit of, or what the limit of this is theta approaching 0. Theta approaching 0. And then now theta here. So now, you have to somehow, you know what? So now let me write this here. This is 1 minus cosine theta. Oh, you know what? I should be using x because the theta. I don't have a theta key, so it's making it a little bit difficult. But next time, I guess I'll use the variable x, okay, instead of theta. So we have this here. Now the thing is this. Now we know that we need to apply this formula right here. So the question is, how do we create this sign? Because in order to apply this formula, we need to create this form here. This is the form which we need to create. We need theta over theta or sine theta or sine x over x. It can be any variable. So in this case, you know what we do? Here we have 1 minus cosine theta. We will multiply by what I call the trig conjugate. Again, I call this the trig conjugate. What is the trig conjugate? Now we need the sine x. If you have if you just leave it as cosine theta, then we cannot apply the formula because the formula involves sine x and x. In this case, what we do, we now multiply 1 plus sine 1 plus cosine theta. So 1 plus cosine theta is what I call the conjugate, the trig conjugate of 1 minus cosine theta. So let's do 1 plus cosine theta right here. So if we do that, then now let's see what happens. Yeah, we are not ready to plug in yet. You're not ready to plug in yet. Okay, so now what is this? Then you now do that. Then what is this here? Then this is equal to now this, the limit. Then theta is approaching 0. The denominator, there is no change. We just leave it as theta, and then times 1 plus cosine theta. Again, if you're not sure, don't multiply these things out. Do not multiply. Just leave it alone, unless you have a good reason to multiply. So in this case, 1 minus cosine theta, 1 plus cosine theta conjugate. So yes, we do need to multiply. So in this case, we get sine square theta. So we have sine theta. And I'm going to write the sine theta separately, times sine theta. And now, when you write it like this, then now this will be done. Let's split the limits now. What is the limit of sine theta over theta? Can you tell me? What is the limit of sine theta over theta? Well, basically chopped into 3 parts. What is the limit of sine theta over theta as theta is approaching 0? What is that?
1.
Here. What is it?
Is it 1?
It's 1. So here we are applying a special rule. We are not plugging 0 to make it 0 over 0. Yeah, we know that that's a 0 over 0 form. But sine theta over theta, we have shown that this as a group is actually a 1. So that guy's got approaching 1. So now, when you split the limits here, let me put a big question mark here. We are still not sure whether the splitting the limits will go through. That is, applying the limits separately. Will that go through? We are not sure. So let me put a big question mark here. A big question mark, because we are not sure whether this will go through. The splitting the limits will go through. That is, applying the limits separately will only go through if the final expression we get makes sense. And we do not get any of the indeterminate forms. So this one, if you do that, then we get a 1 here, 1. And at times, what is sine theta? Sine theta, now we look at this guy. What is sine theta? Theta is approaching 0. So what is sine 0? Sine 0 is 0. No problem. Okay, we get a 0. Now what is this 1 plus cosine theta? What is that? Well, theta is approaching 0. What is cosine 0?
1.
Yeah, cosine 0 is 1. And then we have 1 here, another 1. 1 plus cosine theta. Theta approaching 0. So this is approaching what? 1 plus 1, which is actually 2. But yeah, you're right. Cosine theta is approaching 1. And then we have another 1 here. So that's a 2. So we can see that this guy's approaching 1, that guy's 0, and this guy's 2. So we end up getting 2 over 0. We don't get 0 over 0. We get 0 over 2, which is a 0. Does that make sense? So now, therefore, the split is valid. Now it's a check mark. Split is okay. Why? Because the final number, the final answer we get is not any of those indeterminate forms. If you get a form like 0 over 0 or 0 times infinity, something like that, then you have to go back. You cannot apply the limit separately. But after applying the limit separately, everything works out well, and you actually get a number, then that's it. So that's the end of the game. So therefore, the limit of 1 minus cosine theta over theta at theta approaching 0 is actually equal to 0. And so now this theorem is now proven. But when you look at this theorem here, this is just a problem, okay? And it turns out to be 0. Again, on this, to prove this limit, to evaluate this limit, what did we use? We used one formula. This is the formula we need right here. And so like I said over here, for any limit involving any trig functions, what do you need? You need to apply one and only formula 100% time. What is the formula? This is the formula right here. So that's why this limit form is very, very important. If you have a limit problem, it involves trig, and it's an indeterminate form, then you need this formula right here. What percent of time? 100% of time. And do you need any other formula? No, you only need this formula. Get that? You need this for 100% of time. And this is the only formula you need. For any kind of limit problem involving trig. Of course, you need some practice, of course. You need some practice. So it looks like we'll have to get the derivative here. I'm a little bit too slow here, and I'm a little bit concerned now. Okay, so now, you know what, but I think we need to have a break. The time is 9:50, so let's take a 10-minute break. A 10-minute break, we'll start, we'll what, 10-minute break, we'll continue at what, 10 a.m. 10-minute break. All right? Okay, I'll be back in 10 minutes. All of you have a 10-minute break. Okay, we have, I'm back here. We still have about 2 more minutes to go. Anybody has any questions?
Yes, just one moment. Let me just go back and check the file. Do you know why sine theta over 1 plus cosine theta equals to 0 over 2?
Okay, what is the question again? What sine theta what?
So during the previous example, you showed sine theta times sine theta.
So you're talking about the file A, okay. This is this file? Okay. Oh, yeah. You talked about example 1? No, not example 1. Which one was it? This theorem right here?
Yes.
Yeah. So what is the part of the problem you have?
So near the end, for the limit theta equals 0, 1 minus cosine theta over theta, the answer became 0. However,
Right.
at the end,
Yeah.
At the end, it became sine theta squared.
Yeah. So
over
the sine theta, and then I actually wrote down sine theta except for sine theta here. And then I wrote over 1 plus cosine theta here. And then we have theta here. And this was it, the limit. And then we have the whole thing, the limit as x, so theta is up to 0. Yeah. I think this is what we had before. So what is your question about this guy?
So I understand how sine theta over theta will equal to 1. Yeah. However, I don't understand how sine theta over 1 plus cosine theta equals to, I believe, 0 over 2.
Okay. So basically, let me now color code here. Let me go by, let's say, we go by this guy. Tan theta right here, this, when theta is approaching 0, this guy is heading to what? This guy is heading to 0. Is that clear? And then now let me color code. Now let me change to blue. Now what is this guy going to? When theta is going to 0.
It would equal to 1 plus
1. But this is 1 plus cosine theta, and cosine 0 is 1. So this guy is actually going to 2. So it's a 1 plus. Cosine theta is heading to 1. Cosine 0 is 0. Cosine 0 is, cosine 0 is 1. Cosine 0 is 1, and therefore, theta is approaching 0, cosine 0 is 1. So this cosine theta is heading to 1. And then we have another 1 right here. So that entire factor is actually going to 2. Does that make sense?
Yes.
Yeah. And then obviously, like you said, the sine theta over theta, that's the part which we just learned. Let's say maybe color code this to brown. This guy is obviously heading to 1. So what is the whole thing going to? The whole thing will be approaching 1, will approach 1 times 0 over 2, which is 0. Sense? Equal to 7. So what is the question?
No, I figured it out. Thank you.
Is that clear now? Okay. And now let me now help you understand this theorem right here. Now, many students, they know this theorem here. All of you know this theorem, but students don't know how to apply this theorem. So now when you look at this here, so it says here the limit, and then what? Theta. We have, let's say, sine theta. And then theta is equal to 1. So what I would like to say is that this is heading to 0. Now what I'm going to say is this. I'm going to write the x here. Let me write this in red. I'm going to write the x here. X goes to 0, and this is sine x, and then over x. So the limit of sine x over x at x goes to 0 is equal to 1. Now what you have to understand is that in order for you to apply this theorem, what must be the case? What must be the case is this. This x and x and x, they must be exactly the same. So when you have this theorem, this is the way you should understand. So I'm going to now take all this back here. I'm going to say this. I'm going to, write a block here. So that block could be x, or it could be y, or it could be any other letter, or it could be 2x, or it could be x squared. So when you see that formula, so the formula is this formula here. Let me write down the formula. The formula is this: the limit of what? The limit of sine x. The limit of sine x over x. The limit of sine x over x. X approaching 0. When you see this formula, again, this is the way you should understand. When you write x here, all it means is that these three x's, they must match. This x, and this x, and this x, and this x right here, they must match exactly. As long as these variables match exactly, then the limit is 1. If they do not match, it is not 1. Is that clear? So limit of something, so that something, what could that something be? That something could be, of course, it could be x. It could be w. It could be any other letter. But it could also be 2x. It could be what? It could be x squared. It could be anything. And this is the part which many students do not understand here. So now what I'm going to do now let's go down, and then we are going to do some problems here. So I'm going to save this and then clear all this. So now, we have not done the derivative yet. So this theorem, I'm going to hold it off a little bit. I'll go over that a little bit later. And now, let's look at example 1. Example 1. Example 1. Evaluate. Limit of sine 3x over sine 4x as x goes to 0. Now, what is this? Now we are trying to example 1 here. What is this limit? Well, first of all, we have a limit. So what is the first thing we want to do with this limit? What's the first thing we do? On any kind of limit problem, what do you do first? Well, since we're dealing with all these continuous functions, sine 3x is a continuous function. Sine 4x is also a continuous function. So therefore, what do you do? Plug it in. When you plug in x equals 0, what do you get? We get 0 over 0 form. So that means we cannot plug it in. Now, this is a limit involving trig. Is that a limit involving trig? Is that a limit involving trig? Yes or no?
Yes.
Yes. And it is an indeterminate form, right? So now what do we need? Then in this case, we need one formula. What is the one formula we need? We need that formula right there, which I mentioned. The limit. The limit of what? The limit of sine x over x. Sine x over x. Sine x over x as x is approaching 0. Is 0. This is equal to what? 1. So that's the formula we need, and this is the only formula we need. Again, when you have if you have any kind of limit involving trig, then this is the one formula you need, and you don't need any other formula. This is the only one you need. That's a big hint, all right? Okay, so now we have a limit, example 1. Limit sine 3x over sine 4x at x equals 0. So that is a 0 over 0. So is this equal to 1 also? No, it's not 1. This is not 1. Cannot apply the formula here. It's not in the exact form. If you want to apply the limit, if you want to apply this formula, this must be exactly in this form. The only thing is that instead of x here, this x can be what? Can be anything. So let me block it off. You know what? How about this? What I'm going to do is I'm going to maybe write it in green. This x doesn't have to be x. It can be anything. But these boxes, they have to match exactly. If they don't have exact match, then the limit is you cannot apply this limit. So instead of x there, I put a box there, the green box. Again, what can the green box be? The green box can be anything, any variable in any function. Okay, so how shall you apply this? Well, you look at this form, sine 3x over 4x, sine 4x. So you know what? We need to have this guy. So what we want to do is this. We want to say that we want to do this. So this is not equal to. Now let me make this guy a little bit thinner. And so now let's see, what is this guy here? This is now going to be the limit. The limit, x approaching 0. But now what we're going to do is this. Let's split the limits here. Okay, now I'm not going to split the limit yet. Let's rewrite. So what we want to do is I'm going to write this. I'm going to write, okay, so let's see. This is going to be sine 3x. So this is going to be sine 3x. Oh, well, not purple. Purple's nice, but... And then times what? Let me write 4x. And then times, and then let's see, 4x, 4, so split this, sine 4x, so 4x, so it looks like we need, what do we need here? 3, and then this guy is going to be 3x times sine of 4x, then times 4. So you may wonder what I'm doing here, so just bear with me. I'm going to explain to you what's going on. So this is what I did. By the way, the star means times, okay, in case you didn't know. Okay, when I type these things here, the star means what? Star means times, okay? The star, asterisk is times. This means times. It is what? Times. This is what? This means multiplication. Means multiplication. Multiplication. Okay? Okay, times multiplication. Okay, so now let's look at this. So we have the original expression, the original argument of the limit is sine 3x. Sine 3x over sine 4x. So what I'm going to do is this. So we have sine 3x over 4x right here. So this is sine 3x, and we have sine 4x. That's what we have originally. Now, but in order to apply this formula, we need to match this guy and this guy here. We need to match these guys. Now, do we want to apply the triple angle form of sine? And do we want to apply? Do we need to what? Do we need the triple angle formula? A triple angle formula for sine of 3x. Do we need this guy? So sine 3x is going to be what? Sine cube x in the minus 4, sine cube x or something. You know, there's a sine triple angle formula. You can find that out. But do we need that triple angle formula for sine here? And the answer is no, you don't need that. If you do that, you'll be wasting 20 minutes of your time, and plus you'll probably make a mistake. It's very costly here. So be careful as to what you do. So now the only thing is, when you see the problem, when you see the limit here, sine x over x at x equals to 0, it does not mean that we need sine x. We have a sine 3x, so how can you apply this formula when you have sine 3x, right? The question is, you have sine 3x, we don't have sine x. Does that mean that we have to expand this and rewrite this in terms of sine x? And the answer is no, we don't need that. We don't need sine x. If you have sine 3x instead of sine x, we can still apply it. The only problem is that we need to have this limit in that exact form. So what we need is that the sine 3x, we need this guy. What do we need? We need 3x. Why do we need 3x? Because we need to apply this form. And if you want to apply this form, we need this guy, this green, and this green match. Eventually, we also need to match this guy too. So right now, we have sine 3x over 3x. So we kind of included a 3x there. I put it in. But that 3x is not free. But now let's look at sine 4x in the denominator. We have sine 4x. In order to apply that limit formula, of course, that limit formula is this one and the other guys as well. You can also apply this guy to the same thing. Sine 3x, sine of what? X, and over x over sine x is what? A limit x up to 0. This is also equal to 1. You can also apply the tangent version as well. You know, the other two guys, they're all the same. You can also apply the formula with a limit x over tangent x or tangent x over x. Any of those formula, I will accept them. But anyway, you know what? Basically, I want all of this either apply this or the other formula is this guy here. They're all the same formula.
Could you explain what you just did?
What did I do?
Why did you multiply with 4x into 3 and then 3x into 400?
I'll do that. I'm trying to explain that right now. So we have sine 3x and sine 4. That's what we have. So basically, let me mark this in black. We have this guy here and this guy here. That's what we had before. That's the origin expression. But in order to apply this formula here, we know that we have a sine 3x and a sine 4x here. But our goal is to apply this formula right here. But if you want to apply the formula, what do we need? We need to match this guy and this guy right here. The green must be matched. If we do not match these guys, we cannot apply the formula. So we have a sine 3x. What do you think we need in order to apply the formula? We need to have that 3x. Why 3x? Because we need this form right here. We need this form. Where this green part, this guy and this guy, they match. But putting the 3x there is not free. So we'll hold on to this. So that's why I circled in red. The 3x is something I added there. I included. But it's not free. Okay? So now let's hold it off here. And now let's see. Now we see the next guy. We see sine 4x in the denominator. But in order to apply the sine of this formula again, we need a 4x in the numerator. We need this guy here. Why do we need the 4x here? Why? Because we need to apply this formula again. In this format, in this case, sine says sine x over x is now sine is in the denominator, but we need to know we now want to apply this guy here. So we need a 4x as well. So we need the 3x and we need the 4x. But is the 3x and the 4x free? No, it's not free. So we added the 3x here, but this is all multiplication, and then we added the 4x there, but this is all multiplication. So now, in order to compensate, we have to multiply by 3 over 4. So now, when you look at all the red parts here, all the red factors, look at all the red factors. Do they get multiplied to 1? Do you see all the red parts? When you multiply all the red parts, what do you get?
You get 12x over 12x.
Yeah, which is 1. So now the question is this. Algebraically speaking, is sine 3x over sine 4x equal to this whole thing right here? Are they algebraically the same or not? It's sine 3x over sine 4x. That's the original argument of the limit. Is that algebraically equal to this and this big green box right here? Are they the same?
Yes.
This green box and the top green box, sine 3x over sine 4x. Is that equal to this big green box over here down here? With all the 3 and the 4 and everything here, are they equivalent? Algebraically, are they equivalent? Question is sine 3x, class, sine 3x over sine 4x. Is that equal to that big box out there? Big box where you see. Is that equal? Do I have to write this whole thing again? There's 2 boxes. I don't want to copy this all this, okay? But what I'm saying is this big box in green right here, the big box in green, is that algebraically the same as sine 3x over sine 4x? Is that the same or not?
Yes.
Yes, they are the same. So now I can move on. Limit of sine 3x over sine 4x is equal to the limit of x up to 0, and then there's this big box right here. This big box is the same as the sine 3x over sine 4x. Now the question is, why did I make this big box so complicated? This sine 3x and sine 4x so complicated? Why? kind of looks complicated. The reason is this. Why did I put a 3x there? Because I need to match the 3x in this x. Why? Because I want to use this formula here. This is the formula I want to apply. Then why did I put a 4x there? Well, same thing. I want to apply this formula here, which is really the same as this formula, so I put there. But then if I just put the 3x and the 4x, it is not algebraically equivalent. So at the end, to compensate the 3x and the 4x, I put a 3 and the 4, 3 over 4. So now the big green box is now algebraically equivalent to the green box which we started with. So this is now the end of first step. Everybody understand what I did here? Everybody understand what I did? I put a 3x there because I need to assign 3x over 3x. Why do I need a 3x there? Because we want to apply this limit right here. This is the formula which we want to apply. Which formula? This formula right here. Am I shouting? This is the formula which we want to apply. This guy right here. Why? When you have the limit of any kind of limit involving a trig function, this is the formula we need. What percent of the time? We need this formula what percent of the time? 100% of the time. And this is the only formula you need. Is that clear? This is the only formula you need, and this is the one formula you need. You need this one formula, this is the only formula you need. But if you want to apply the formula, this green box right here, the sign of something, 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 or the parts which are marked in green, they must be exactly the same. Otherwise, we cannot apply this formula. We cannot. So we have to artificially equate this 3x. Why? Because we need that form. And we also need that 4x there. So we can apply that form right there. So this x and this x and this x, they must match exactly. Okay? So, but then 3x and 4x are not free. So we have to compensate all the red parts here. They all get to be the factor 1. So 4x times 3 over 3x times 4 is 12x over 12x. So now we can now put that 3 over x there. Then now they're algebraically equivalent. They're algebraically equivalent. It has to be algebraically equivalent. If it's not algebraically equivalent, then you cannot do it. So 3x is not 3. We need that 3. So all that thing, so equal to 3 over 4, now it's algebraically equivalent. So now we're almost ready, but not quite. Now if you look at this expression here, we have sine 3x over 3x. So this guy right here, this guy, you know what? Let me write this in orange now.
Yeah, exactly.
This guy right here in orange is this guy is a box there. This orange part right here, and this guy right here. Now we have a match here. But one thing is still not matched. This guy's not matched there.
Well, it's actually
We need a triple match. Again, you don't apply this formula. What do we need? We need a triple match. This guy, this guy, this guy must be exactly the same. Exactly the same. A little bit different, not one, doesn't work. So now let's see. We have a 3x. Now let's see. The original limit is x is approaching 0. But when x is approaching 0, you know what? When x is approaching 0, what is happening to 3x? When x is approaching 0, can you tell me what happens to 3x? Oops. Back. And this one. When x is approaching 0, when x is approaching 0 here, what is when x is approaching 0, what is happening to 3x? What is happening to 3x? In other words, what is the limit of 3x? What is the limit of 3x when x is approaching 0? Can you tell what this is? What is the limit of 3x when x is approaching 0? Can you tell what this is?
0.
0. So what I'm saying is this. When x is approaching 0, this implies that 3x is also approaching 0. So the original limit says x is approaching 0. But what we do know is when x is approaching 0, 3x is also approaching 0. And that is not so, it's not so difficult to understand that. When x is approaching 0, 3x is always approaching 0 as well. And then what is happening to 4x then? Well, it turns out 4x is also approaching 0. So when x is approaching 0, 3x is also approaching 0, 4x is also approaching 0. That's what it means. So x is approaching 0 means 3x is approaching 0, also means that 4x is approaching 0 as well. So now we have a triple match. What is the match here? We have sine 3x over 3x, and 3x is approaching 0 with this guy right here. Now we have a triple match. This star here, and this star here, and this star here, we need a triple match. If we don't have a triple match here, this limit formula cannot be applied. So we are not ready. So what is happening to sine 3x over 3x? At 3x is approaching 0. That's 1. That's a 1. Now what is happening to this 4x over sine 4x as 4x is approaching 0? Now we are using this version of the limit. That is also 1. Done. And then we are left with 3 over 4.
So you're saying we can transform what the limit is approaching as long as it approaches the same number no matter what the x is?
Yeah. As long as these this star here, in the formula here, I have a star here and a star here, a star here. As long as these 3 stars is a match, it must be x. This star could be x, it could be w, it could be z, it could be 2x, it could be x squared, it could be x cubed. This star could even be sine x, it could be anything. You know what I'm saying here? As long as you have a match here, this guy, and this guy is a match, then you can apply this limit formula. Right now, the first part, we let the star be 3x. So sine 3x over 3x, the 3x over 0, that's 1. So I wrote that a 1 there. Next guy is times 4x over sine 4x. Now we are applying this version right here. We have a triple match, 4x, 4x, 4x. Yeah, triple match right there. So that goes to 1. And then now after that we have 3 over 4 left. So the final answer comes out to be 3 over 4. Everybody get this? You get that?
Yes.
Okay, now we need some more practice. Let's do example 2. Very similar arguments. I cannot do too many of these, but you know what? I'll do a few. So what I'm going to do is now I'm going to erase a little part of it. Let me erase this part right here. Maybe I should not. Okay, you know what? Maybe I'll erase this. I think this much is a little bit. I think I wrote it there. I did write 3x is approaching. So now let's look at example 2. Example 2. Okay, so let's look at this. We have a limit from here. Limit of what? Limit of 1 minus cosine 2x over x squared. Okay. So now what is that? That's the limit. When you have a limit problem, what's the first thing you do? What is the very first thing you do on any limit problem? What is it?
Plug in.
What do you do? On any limit problem, what is the first thing you do?
You plug in.
Plug in. That's right, plug in. When you plug in, what do you get? This is cosine of 2x, by the way. Cosine of 2x. Maybe I should put a parenthesis there. It's cosine of 2x, not cosine 2 times x. It's not that. It's cosine 2x. Okay, so when you plug that x equals 0 there, what do you get?
You get the 0 over 0 form.
That's right. You get the 0 over 0 again. By the way, it is not in now when you plug in this x equals 0 and you do not get this indeterminate form, then you know what? Then that means the game is over. Then you don't have to do anything. The game is over. You either get infinity or you get a something, or you get a 5, or you get something. But if it's not an indeterminate form, the game is over. You don't have to do anything. You just have to plug it in, and then whatever you get, or you might get if you get 3 over 0 plus or something, then that will be infinity, and then things like that. But in any case, you plug in, and then you get what, and then it's over. But when you have an indeterminate form, then this is when you have to work harder. If you do not get an indeterminate form, then the game is over, basically, essentially over. You plug it in, and whatever you get the answer. That's it. So the hard case is when you get an indeterminate form. So if we get this indeterminate form, now we look at the limit here. What do we see? Oh, we see a cosine function. Okay, now. So once you say cosine function here, a trig function or any trig function, including sine, cosine, tangent, cotangent, cosecant, whatever. Out of all the 6 trig functions, if you have anything, then now what is the formula you need? You need this formula right here. And this is the only formula you need. Is that clear? How many times do I have to say this? You need this formula, and this is the only formula you need. You do not need any other formula. Of course, if you have this one here, that's good. We can have that one too. This guy is like essentially a variation of this guy. Okay, because sine x over x is basically same as 1 over sine x over x. So essentially sine x over x, this guy is heading to 1. And then the numerator is 1, so that's why it's 1 over 1, which is 1. Essentially the same guy. So you are free to use this one or that one, or the one with tangent. You know what? How about this? Let me skip the tangent. Just use these two, okay? All right, now let's see. What shall we do now? So we want to use that formula. But if we want to use that formula, what do we need? With this cosine in there, we cannot apply this formula. So if you want to apply the formula, we need to create this form right here. We need to create that form. So how do you do that? So this is now equal to the limit. The limit, what is that? The limit x approaching 0. We have x squared here. And this is going to be what? 1 minus cosine 2x. So let me type that in.
Would you multiply by the trig conjugate?
Yes. What is that? What is the true conjugate of this guy? Said it right. What is it? 1 plus?
Cosine.
Yeah, this guy is the conjugate. And you're absolutely right. We multiply by the trig conjugate. And of course, we have to compensate, and then we have to multiply the same to the denominator as well. Because 1 plus cosine 2x is not free. So whatever you do to the numerator, we have to put that to the denominator as well. So we end up getting this guy. Okay, so we have this. So we have this. Okay. So now, because they're conjugates here, let's multiply it out. If you multiply it out, what is 1 minus cosine 2x times 1 plus cosine 2x? And that will be what? That will be what? 1 minus cosine squared 2x. And what is 1 minus cosine 2x? What is 1 minus sine squared x? That will be 1. Well, that will be 1 minus cosine squared 2x. And 1 minus cosine 2x. 1 minus cosine squared 2x is actually sine squared 2x. So that is equal to, now let me write that down. That will be sine 2x. And then that will be what? A square. And then I have to multiply square that and square that. And that will be 1 plus. Oh, no more 1 plus. And then the denominator will be x squared. The denominator will be x. Let me put the x here. That will be x times and the what? And when the x plus 1 plus, and then cosine, and then 2x. And then basically, this is what we get. Now I need to put the square here. Bear with me here. You get this. If you multiply the entire numerator, 1 minus cosine 2x times 1 plus cosine 2x is 1 minus cosine squared 2x, which becomes sine squared 2x. Yes or no? Okay, so we are kind of ready. We have done more than half of the problem at this time. I should say we have done about 70% of the work at this point, but it's not done yet. Because when you see this here, now we have sine 2x. Oh, we don't have sine x, we have sine 2x. If you want to, apply this formula, our goal is to apply the formula here. Then we have to match this here. X, x, x. We need a triple match. The star, star, star. Right now, we don't have a match here. So now, we need to go through that tiny procedure again. So what is the procedure? The procedure will be this. The limit here. And note that we also have a square. So what I'm going to do is now this. What I'm going to do is now, this right here. I'm going to now put sine square of 2x, so I'm going to do the sine of 2x.
Vector is not virtual speed.
It's not?
And then this. And then in the denominator, what I'll do is I'm going to put
They have a
x. I'm going to put x here.
Remember when you was
And then I'm going to put this right here. 1 plus, and the what? The cosine of 2x.
This is terrifying.
Oops. You know what? This part is kind of ugly, so let me now erase this part right here. Oh, I don't want to erase that. Oh, what did I erase? Can I erase what I want to erase? There we go. Oh, erased the wrong thing. Oops. I'm erasing the wrong thing. Sorry. I want to erase this stuff. Oops, I can't erase that one. You know what? I'm sorry. So let me just do it this way. I have to just write a message. I'm going to do this. And I'm going to erase all this right here. Because we don't need this stuff. I'm going to just back out. Okay, what is this one? I'll just back out this guy. So again, it's bothering me. I can erase this thing. So let me just do this. And it's kind of messy, but you know, this is what I can. And then now what I'm going to do is I'm going to do this. I'm going to put a square here. Now, does everybody understand here? What I did was I said sine 2x and then square, and then we have x squared here. So why don't I now put a sine 2x over x, and then I put a square of the whole thing. And then 1 plus cosine per sin. So they're still algebraically equivalent. Are they algebraically equivalent? Yes, they're algebraically equivalent. But we are not ready to apply the limit formula there, the limit of the sine formula. Why? Because we have 2x here, x here does not match. So now I'm going to write this in red. In order to apply the formula, what do we need? We need to write a 2 here. We need a 2 there. But if I put a 2 there, we have to compensate. So what should I multiply in the numerator? Can you tell me?
4.
That's right. I need to put a 4 here. That's because even though I have a 2 here, this 2 is actually under the square. So we are actually putting a 4 in the denominator. So now, if I put a 2 there and a 4 there, then now it is a full match. Then that means it is now equivalent. What that means is this green box right here, this guy right here, it is now algebraically equivalent to this guy right here. They're algebraically equivalent. You said that they're algebraically equivalent? Yes or no? Are these two green boxes algebraically equivalent?
Yes.
Yes.
Yes. We put a 2 there and we put a 4 there. Now the question, why did I put a 2 there? Why? Because we have sine 2x. Our goal is to apply this formula. If you want to apply this limit formula again, we need a triple match. Especially we need to match this guy and we need to match this guy. So we have a 2x. And by the way, sine 2x, can you apply the formula? Yeah. I'm sure that all of you know the formula. Sine 2x. Sine 2x is sine double angle formula. This is equal to what? This is equal to 2 times sine x, and then times cosine x. The question is, do we need this formula? Do we need this formula?
No.
Can you apply this formula? Need this formula? That's the question mark here. Now remember, in math, let me tell you the rule. If you learn a formula, then the first thing you have to learn is how to avoid the formula. Is that clear? That's the rule. It's like taxes. You learn taxes. So why do you learn taxes? So that we don't have to pay taxes too much, right? Or we don't want to be legal. But in math, when you learn a formula, the first thing you have to learn is how we can avoid the formula. Okay? So don't be too happy to apply the formula. So can you apply this double angle formula? Yes, you can. If you apply double angle formula, you can get this. In this case, it's not too bad because it's sine 2x. So remember, do you think on the test, do you think I'll give you on the test, or quiz, on the test, will you see sine 2x? Do you think I'm going to give you sine 2x on the test? No. You know what I'm going to give you? On the test, Or am I going to give you this? How about sine of 55x? Am I going to give you this? Which one is more likely to show up on the test? Sine 2x or sine 55x?
55x.
That's right. That's what I'll give you. I'm not going to give you sine 2x. Or am I going to give you sine 2x? I might give you sine 2 times square root of x. Or square root of 2 times x. Or I will give you, or what? I will give you this. Or how about this? I'm going to give you a fraction. Sine of, and then this. And then I will give you this. I will give you this. And then I'll give you sine 3 over 2x. Oh, let me, what is this here? Undo, and then this one here. I will give you sine of 3 over 2x, like this. So, when you see sine 2, when you see 2x there, don't think that you will always see 2x there. That 2x on the test could be 5x, 55x, or 3 over 2x. It could be 1 over 10x. It could be anything. So I want you to prepare. So the best thing to do is, when you see sine 2x, do not apply the double angle formula. Okay? The double angle formula works in this case. By the way, you can try this by applying the double angle formula. I think that's a good thing you should try. But on the test, that is usually not the way to go. You don't want to waste time doing this kind of thing here. Or even though sine double angle formula is easy. Okay, now we come to this guy, and now we have a sine 2x, so we have to match this guy. We have a 2x here, and now we have a 2x here. Now these guys are matched. But this limit of this guy, the bottom guy, is not matched yet. So now same thing happens. X is approaching 0. If x is approaching 0, then what is happening to 2x then? Well, 2x is also happening is going to approach what? 0 as well. This is not hard to see. So sine 2x over 2x, and 2x is also approaching 0. When x is approaching 0, 2x is also approaching 0. Now, looks like the game's over. So when you now plug this in, question mark, can you now plug it in? Yeah, let's see. Well, what now we are going to split the limits here. What is happening to the sine 2x over 2x at 2x approach 0? That whole thing becomes 1. So then the 1 squared. 1 squared is 1 anyway. So times. And a 4 is there. And then what is the bottom guy there? What is happening to this guy? What is that?
Does that become 1 plus 1?
Yeah, that's going to be what? 2.
1 plus
1. And what? Final answer is? And can you check this number 2 using a calculator? Oh yeah, you can use a calculator and check this guy. So let's say you go back to limit here, and then plug in x equals what? X equals 0.00001, and when you actually plug that in, you will get a number very close to 2. So you can verify by estimation. Again, using a calculator, you cannot write the answer. I'm not going to accept that. But using a calculator is a very useful tool to verify your answer. Okay? So that's the best way to check. Or you can actually use a graphing calculator and just graph this guy and see what happens when x is approaching 0. So you can go to decimals and plug that in. And when you actually, plug that in, draw the graph, and you can figure out what happens to when x is approaching 0. So either side. And you can see that the graphs are actually approaching what? 2. Okay, you can see that. But again, the graphs will not be acceptable on the test. Okay? So that's okay. So now let me save this now. Okay, now clear this. I'm going to clear this. These are the only 2 examples of the limit problems we have here. However, let me just show you. If you close this file and open up limit trick 1, this file, the very next file, when you open up this file, you have many other problems here. So look at all these problems here. You know what? The earlier problems you don't have to do, but the ones which are interested in number 7, problem number, how about number 6, number 7, number 8, 9, 10, 11, 12, you have all of these problems here. So you can do here number 14, part A, B, C, D, all as well. You have tons of problems here. So I added a few because I only did equal 2 problems here. And if you go to limit the second file, limit trick 2, and this is another page where you have a lot of problems here. And so you have plenty of problems here, okay? By the way, when you have a function like secant, don't worry. Convert that secant into 1 over cosine because we can only, we know everything about sine and cosine, so that's the trick, okay? So when you see cosine and secant and cosecant, don't be scared. And then our trick is, what happens to a limit like number 7? If you see number 7 here, am I sharing this page? Yes. If you look at this number 7, Number 7, the cosine of 6 minus pi over 3x as x approaching infinity. So when x approaches infinity, how we apply the limit formula? Because our limit formula says x is approaching 0, right? So in this case, what you do is you have a trick. The trick is this. When you have x is approaching what? X is approaching infinity. You know what? In this case, left, x is equal to 1 over w. And then if you do that, then x is approaching infinity now gets converted to w is approaching 0 plus. Okay? And then now you convert all the x's to w's. And then when you convert all the x's to w's, you get a w limit in w. And the w will be approaching 0 plus. And if you have a w approaching 0 plus, then you can apply the sine formula. The limit formula on sine is the two-sided limit. So when you have a limit of limit of sine, this means that we have a two-sided limit. So can you apply this formula where x is approaching 0 plus? Is that okay? So yeah, this you can apply. If you want to, you can just apply this formula. 0 plus is equal to 1 as well. If the two-sided limit is 1, the both one-sided limits are also 1 as well. So this is also true. And if you have a 0 minus, that's also true too. You have a two-sided limit. A two-sided limit is better than the two one-sided limits. And then that's how you convert the x's to w's. Why w? Because when you convert that to w's, then now you get the zeros. So there are all kinds of substitutions you have to do. So if the limit is, if the variable under the limit is not heading to 0, then you have to change that so that the variable will be approaching 0, and that is something you can do all the time. Why do you want to let this variable approach 0? Why? Because we want to apply this formula. That's basically the rule here. Unless we will convert this formula to something where the 0 is x approaching infinity, yeah, we can do that too. But usually we don't change the formula, we change the problem. Again, we don't change the formula, we change the problem. And then we have many more problems here. So you know what? I want you to try all of them, and you have to make sure that you can do all of them. All right? So I'm not going to I cannot do any more problems at this point. But anyway, I think I have spent enough time. But you have more problems there. You can need more problems, okay? So make sure you can do all of them. So that's the end of that. And now let me go back here. We have only a few more here. And now I'm running out of time again. I'm not sure what to do here. Am I spending too much time? Yes, here. Now what we have to do is this. We have this limit here, and the limit here, and now we have now let's go to this here. Now here comes the definition of the derivative of sine. You know what? Wrong file. Let me open the other file. 072b. I know we have only about 4 minutes left here. Now if you look at the bottom here, now we have the final theorem. The key theorem on this section here, right here, is this guy right here. Theorem is this guy. The derivative of sine theta is equal to cosine theta, and the derivative of cosine theta is equal to minus sine theta. So what is the derivative of sine theta? Right here. And now, sine theta, now what is the derivative of sine theta with respect to theta? So now this is the limit of h approach 0, sine of theta plus h minus sine f. So we get this. This is by the definition of the derivative. The first step is very important. So if you let this sine theta be f of theta, if we call that f of theta, then what we need is we need f of theta plus h, which is sine of theta plus h and minus sine theta over h. And then now we have the sine of theta plus h. Now here we need some trigonometry here, a trigonometry formula. The sine theta plus h happens to be this guy right here. I did ask you to review your trigonometry. And again, you know what? I was not your truth teacher, so I don't know how you study your trig, but anyway, these are the formulas you need. Now here, what you have to watch out is you have to distinguish the theta and the h. It is very critical that you distinguish the theta and the h. And note that in this case, h is the variable. H is approaching 0. But theta is considered to be constant. Theta is constant. Theta is approaching, h is approaching 0. So now, now we have this here. So now we have the limit of this guy right here. So now, if you look at the next line, I have split into, I have written that argument into a sum of two here. So let me erase this. So let's look at this again. Okay. So now this guy right here, that is equal to this guy right here. They must be algebraically equivalent. So how do I organize this? What I did was the terms which have the sine theta in it, the terms which have sine theta in it, I grouped into one term, and then the term with cosine theta in it, I grouped that into another group. So we end up getting this. So algebraically, that's how you see it. Now note that if h is approaching 0, so what is theta? Theta is not a variable here. Theta is a constant. So this is now equal to, maybe I skip one step here. This guy is actually equal to sine theta. Sine theta is a constant. Again, you have to understand the difference between the h and the theta. H is a variable. H is approaching 0. Theta is not approaching 0. Theta is just a constant. So we get this. So now the question is, what is happening to this guy right here? What is the limit of cosine h minus 1 over h? What is that? Can you tell what the limit of that guy is? Oh, that guy. Oh, it's over here. Yeah, actually did this guy. It's actually over here. This guy's actually what? 0. The plus. Then we have cosine theta. And then what is the sine h over h? What is that guy doing? Can you see the last part? What is sine h over h?
1.
That's a 1, that's right. So because of that formula we need, so that's 1. And so when you multiply all that, what do you get? Is cosine theta. So we end up getting the derivative now. So this is actually the proof of the derivative of sine theta, or sine x, or sine. So what we have is, many times actually, instead of theta, we actually use the variable x. So the derivative of sine theta with respect to theta is cosine theta, or simply, the derivative of sine x with respect to x is what? Basically sine x. If you have a sine x here, and the derivative function, what is the derivative of sine x? Is equal to what? Is equal to cosine x. And then, in a similar way, the derivative of cosine theta is sine theta, minus sine theta. And the proof is actually very, very similar to the derivative of sine. And then these are all the formulas here. In order to prove these formulas, what is that you have to do? You need to know these formulas here. You need to know the derivative of sine and cosine. And plus, you need what? Need the two formulas. Need particle and the what? Quotient rule. That's what you need, okay? So quotient rule. And then if you have those two formulas and then need the product and quotient rule, then you can prove all of these formulas here. Why don't you prove them? You prove them, all right? And each formula will take about, 2 or 3 minutes. It really doesn't take that much time. Again, I'm telling you all the ingredients. You need to know the derivative of sine and the cosine, and you need to know the product and the quotient. That's all you need. And then you can prove this. You don't have to start from by the definition. You can prove these formulas by using other formulas. Okay, the time is up here. Let me stop here. And this section is over now. Please do the rest of it. You know what? We have many more problems here on this section, but you are now ready to do all of this. So let me just scroll this down. Example 3, yes. Example 4, yes, you can do that too. Example 5, yes, you can do that too. And do all of these, okay? So when you come back tomorrow, we will be starting the next section, which is a chamber, all right? Okay, all of you have a good day, and I will see you tomorrow. Goodbye, everyone.
Professor, our next test is next Monday, right?
You know what? I'm not sure. Okay, I'll make an announcement tomorrow. Okay, I'm not. Okay, we'll see.
Okay.
It could be Monday, but I was hoping to give you on Monday, but okay, I'm a little bit behind schedule here. I'm spending way too much time on all these topics here. Okay.
If we did do it on Monday, should we expect our test after that same week?
If not Monday, then will be Tuesday. If not Monday.
Okay. Okay.
We
And
cannot
then
post.
the test after that, will that be like the following week, or could it be the same week?
No, same week is impossible.
Okay.
Same week is impossible. Yeah. Because you know what? Chapter 3 has much stuff as chapter 2.
Okay.
So, so maybe, more likely, maybe Monday again. Okay? So that's
Okay.
likely.
Thank you,
Same
Professor. Have a
week,
good day.
Okay. Okay, anyway, you know, I will tell you exactly when the test will be. If not Monday, then it will be Tuesday. But anyway, for now, so tomorrow we'll know when the test will be.
Thank
Okay,
you.
does any of you have questions?
I wanted to stay until I'm the last one in class just to talk to you really quick.
Okay. Okay, anyone else has any questions here? Does anybody have any questions? Huh? Okay, what is your name, by the way?
It's Rachel. We talked yesterday. I sent you an email.
Rachel, okay, Rachel, yeah. Okay, you know what? I'm going to break. Why don't we, since there are a lot of people here, okay, I just want to make sure that there's no one else has any questions. Okay, anybody besides Rachel have any questions? Yes, no? Okay, no. So what I'll do is, how about this? How about if we enter a breakout room? Where's that breakout room? A breakout room right here?
Okay.
Okay. So, so that, you know, it will be, or do you want to just talk in public, or do you want me to set up a breakout room there?
Up to you. I don't really mind.
Yeah, if you know what, if this is not a top secret, then we can just, you know, just do it over here in this room. Mainly.
Okay.
Okay, what is your question?
So it's just regarding the email I sent you yesterday.
Yeah. About
the
what is it, solution? Yeah, I saw that solution.
Yeah.
It's about that function, the compound function, right?
Yeah. So the thing is the email I sent you wasn't what I put on the test. It's just to show you that what I put, because when I talked to you about it, you said that you had never seen it before and that I was guessing, right? So what I did was I wanted to show you that the formula I used to get my solution on the test was not guessing, and it was a formula that does exist and does work. So the email I sent you, I think you were responding to it as if that's what I posted on the test, but that's not my solution for the test. That's just to show you that what I did put on the test is justified. So I don't know if you want to pull up my test and then look at my test, and then.
So first question is this. So the question you're talking about is midterm 1. I think was it question 4?
Question 7.
Question 7 is about the compound. Is it about the compound? Let me see the question here. Let me see. Midterm 1. Okay. Question 7. Question 7. Oh yeah, that's about the compound right there. Yeah. So I looked at the file where you had the compound. So and I think I already sent an email. That's
right,
now the question is, did I look at the wrong file?
Yeah, so that's what I'm explaining is the email that I sent you was not what I put on the test. What I put on the test was a different answer, and the email I touched and sent to you was to show you to like back up what I did on the test and show you that it was actually like a formula that was being used and that I was not like making it up or like guessing. So if you look at my test, there's going to be the actual solution, and then the email I attached to you is what I used to like get that solution. Is how did I justify, like why it's justified the way I found the solution on the test.
Okay. First of all, when you take the test, there is no chance for you to justify anything. Okay, so that's the one rule. All the justification must be part of the test.
No,
so
they were. That's what I'm explaining is they were.
Okay.
I just know when I went to the tutoring center as well, she told me that she's never seen that form, like the format I used to do the solution. So what we tried to do while I was in the tutoring center was to like back it up and show that the formula I used to derive the answer is actually justified. So that's what I'm saying. It's like I justified my answer on it, but I don't think you've seen that form of solving before. which is why I attached the email to show you that it is
You know what?
it is possible.
Let me try. How about this? Let me try to open up the file here. Let me see. Is anybody still here?
I think there's like 3 other people in here.
Okay, all right. So now let me see. So what I'll do is, how about, you know what? I don't want to lose you by, you know, clicking the wrong thing. So sometimes when I try to go here and there, you know, I'm not good at this, and so.
You want
I
me
end
to
up clicking.
pull up my test so you can see it? I can pull it up, the solution.
You put it up? Okay,
Yeah,
why
I
don't
can
you
put it.
up?
I can put it on the
See?
screen to make it easier.
Yeah. Okay. Why don't you do that?
Okay.
Sure.
Give me just one moment.
Are you allowed to control the screen? I know
think
that you
so.
can write on this board.
I'm pretty sure I can. Let me try. Let me open it up
Okay.
first, and then that way you can.
Yeah, I still have a lot of things to learn here, and I'm not fully controlling. I don't know exactly how I can let the students, you know, control or disable, you know, controlling the screen. So
Yeah.
I don't know. Do it.
No
Can you do
worries.
it?
Wait. I'm opening up the document first, just so I can show you it. So I can make sure I pull it
Okay.
up, and then if I do this, you can see that, right?
I cannot see anything.
You cannot.
I
It
cannot.
shows that I'm screen sharing. Let me try it again.
How's it going?
Okay.
Okay, so oh yeah, there you go.
See this?
Good.
Perfect.
Yeah.
So this is my
Okay.
yes.
Okay, so that is your answer. Okay, I see. Okay, good.
Okay, that is my
Okay, now,
answer. And I know the way
all
you.
right.
Sorry, what?
Okay, so I see, what I see here is, yes, okay, now here, let me, can I write on this board here?
I'm not sure if you can. I know you
Okay.
did it. I know you already showed me the way that you did it. And I understand the way you did it. I know you just subbed in the equation back into itself. But
Right.
I just wanted to show you that using this method that I used, even though I didn't get, you know, like I know that for f of x, you got x, but I got 4x
Yeah.
minus 1 over 3, x plus 3. So what I wanted to show you is that if I go to our email, you can see the mail, right?
You have to see them.
So if I go to the email, what I'm showing you
Yeah.
here, right, is not, you can just disregard the 4x minus 1. But what I'm showing you here
Yeah.
is that if you use the method I did, that with any function where the denominator and numerator are linear equations, you can just do it the way I did it, and you would get the same answer back. This
You
is
know
just,
what, first of all, you know what, why don't you close it off, and why don't we go back to your screen again, so your test.
yeah, okay,
Now we can make some comments there.
okay, perfect.
Now, this one here,
Oh, you want me to go back to that one?
go back to the page you showed me,
Okay,
the solution page.
yes.
So
Okay.
you're saying that solution page is actually, it's posted on the quiz.
Yes, this
So
is
that
the one
means I
posted on the
started.
quiz. Yes, this is this
This
one.
is the page I looked at already, and I graded it.
Yes.
So there's really not much, there's nothing new here. If this was posted on the test, I already graded this page. I already did. So now let me make some comments about this. About the first line. Now, I don't know whether I can write this or not, so let me see. View options, annotate. Yeah, you know what? I can write it here. So let me make some annotation here. So here, so we start with F compound X. Very good. So you do the calculation. Now the question is, when you do this F compound X, you actually got this.
Right.
So you actually got the function right here. But the question is, when you plug this in, this f of x right here is this f of x.
Mm-hmm.
But the question is, when you apply the second f here, you are plugging this f of x, you are plugging this 4x minus 1 over x minus 4 into the function, and you are using this function. F of x is equal to x over x minus 1.
Yes.
Are you applying this function right here? But this is not the f here. This is a major problem here, because your f is this guy. Why are you plugging in this into this function right here? See, that is a logical problem now. This is the major problem, and so of course, the answer at the end does not work. This is ultimately not true, because you're supposed to plug this f of x. Basically, what you have to do is you have to find this f of x, and then when you do that, you know what you get? let me write on this side, on the bottom right, with a space there. So you must have this. You must have f of x is going to be, let me show you what you should have gotten. You have to plug this f of x into the function f here. You must get this. You must get this. And then put 4 times x,
Right,
and
you,
then
you
minus,
showed me this already. And I know I did it
and
differently.
then x minus 4. But this
Yeah.
is what I need to see. You have plugged this function right here. You are basically plugging this f of x into a function f here. So this f and this f, even though you're using the same name, are actually two different functions. This f right here, the first f, you're actually using this function right here. Where is this function coming from?
So that's what I was showing you,
You cannot specify.
is that
But
in
where
high
is that
school,
function coming? Where is this guy coming from?
well, let me explain.
Well, what is
And,
that coming from? Yeah.
So in high school, we learned this trick where if you plug any function where the numerator and denominator is linear, you can use a basic formula to derive the same answer, which is what I was showing you here, that no matter what you plug
Okay, let
in.
me ask you this. Why don't you just go back to original function?
Okay.
Original function. You know what? Let me tell you this. If you, let's plug in value. If you plug in a 5 into this function, what do you get? This is f of x. What is f of 5? Let me ask you this. What is f of 5 on this function? If you plug in a 5, what do you get?
It's 19.
You get 19. You get 19. Now, if you plug in a 5 into this guy right here, this function, what do you get? What is the function? What is the value of f of 5 for this function?
5 over 4.
A 5 over 4. That is, you know what I'm saying is they're different functions. So I don't know what your trick is. I don't know what your formula is, but there now you're now using a different function. So what is the logic here? You said you have formula. You know what? I don't know what formula you're using, but let me tell you this: your formula is wrong. You know, I don't think your teacher taught it wrong, but I think you probably learned it wrong. I don't think any math teacher would say that this guy is the same as this guy. It doesn't make any sense. This is a different function, and you are using the same name. So if you want to use this function, you should call this guy g.
Okay.
And this g function g will not be the same as function f anymore. But the introduction of this function right here itself is a problem. I don't know where you get this. And again, I don't know what formula you're using. But the fact is, this g is not the same as f. Plug in one value, there are different values here. This f is not this function. X over 1 over x, this guy is a different function. So it is a big question mark here. Not the same function.
Okay.
So at this point, you know what? At this point here, it breaks down. And then of course, f compound f of x, if you do this correctly, you don't get this guy. I guess this one might be correct for this one, but again, this first step right here, this guy right here is already incorrect, this guy. And therefore, at this point, now you're doing a completely different problem. And there's nothing for me to break. I mean, first of all, if you have a function which is different, you should not use the same name. That's the problem. Now, if you want to somehow use the function to do something, at least you should call this guy g. But if you call this guy g, then now you get into more problems because this function is not part of the problem. It's not part of the problem. Your problem is, in your case, your function is this guy. Is there any need for you to introduce function, this new function, x over x minus 1? No, there is no need for you to do that. And this function obviously does not look that much simpler than the original function f. So at this point, we have a problem. This function, are you convinced that this function f is not the same as this f? Are you at least convinced that? Or are you still claiming that this is the same function as this guy? And written in a different way?
I get where you're coming from.
Yeah, this function f, the second guy, this is a different function. And then you also named that by f, and especially you have to find f compound f of x. And then f and that f are different. They're not the same. Again, I have no idea what formula you're using, but you know what? It's wrong. That's all I can say. It's just that it's wrong.
Listen to this teacher.
I don't know where you're getting this from.
Talk about this
And
function for 10 minutes.
And it's just that you don't need this function. Why you are trying to make it more complicated? It is just that simply different. Now, sometimes you have a function, and you can express the function in a slightly different way. But that's only if the functions are the same function written differently. But that's different. Here, you actually have two different functions. Now, you know, but this one here, how do I know that they're different? Because for the original function when x equals 1, it is defined. But this function right here, when x equals 1, is undefined.
Oh,
It's not hard to see that they are different functions. f1 is defined here, f1 is undefined here. So how can it be the same function? Now the question, is that an inverse function then? I don't think that's an inverse function either. This is not the inverse function. Some people, they have actually using using inverse function. And there's a way to do that. But in this class, I didn't do that. But if you did that correctly, you can apply that rule too. Inverse function. But in this case, this function f right here happens to be its own inverse function. So this is not the inverse function. So this f you created here is not the original function. It's not the inverse function. Who's this guy here? This is really nobody. Again, I don't think your math teacher taught it wrong. I think you learned it wrong. Okay? Math teachers, it's a very common problem. Teachers teach one thing, and the students learn it differently. So again, I'm not sure. You can explain to me, but I don't think we need to do that at this point. This is calculus 1 right now, so I mean we are way beyond this level right now. So in this case, you just have to follow the rules carefully. And again, this is not just a different way; it's just flat wrong. I don't know. There's really nothing much to say. And therefore, there's nothing much to grade. And by the way, even if this is true, I don't know how you get to this one. Now you're using this function again, x over x minus 1 again. So are you doing this problem right here, or what is the rule of this guy? So somehow this original function here, you threw this out, and then you are using this function as if this guy is the same as the original f. But like I said, obviously they're not the same function. So again, I don't know. It's just there's nothing much for me to grade here. I mean, you just create another function. To me, this guy is simply another function. I mean, there is nothing much to say here.
All right.
I don't know. I mean, make sense?
Yeah, I get where you're coming from.
Yeah. So in this case, you know what? I don't know how many points I gave you. Did I give you any points? But this one, this solution here,
2 points.
this is already happening right here. So how many points do you deserve? 0. Unfortunately, you don't deserve any points here because you made a mistake at this point. Make a mistake like this at the very beginning will cost the entire problem. Okay, so that's it.
All right. Thank you.
What? Okay, good. Okay, bye-bye. Yeah. Okay, any questions here? Does anybody have any questions? No? Okay, let me now end the meeting and end the office hours. Goodbye, everyone.
Whoa. Huh?